Okay, hi guys, this is Yash, and in this video we'll talk about vector DBs, how to build actual retriever for our RAG module. So in the last lecture we saw what exactly RAG is. In this video I plan to actually complete the whole RAG and implement it, but it was getting too long, so I was missing one retriever part, and that's what we'll discuss in this video. Basically we'll talk about vector DBs and what is semantic search and why do we even need something like vector DBs, and we'll touch upon embeddings as well. So what happens is in the last lecture we saw we need this retrieving of documents. So let's say we have multiple chunks of documents and we have a query. So based on this query we want to retrieve a document from this set which will have the answer to this query basically. So that is the problem of retriever. Now you can think of this problem in a very simple way. Like basically what we can do is like, let's say we take this query, the query string, and we'll see which words are present, and whichever document has most number of overlapping words, you can just retrieve that document basically. So this is a very like a simple retriever that you can think of in the first glance. But what happens is we want to build like a semantic retriever. Let's say for example these documents, let's say they are describing the Llama 2 paper, and maybe one sentence in one of the documents it says Llama 2 has different variants of model. So this is present in one of the chunks, and it continues actually. It goes like talks about different variants as well. Let's say in query we ask something like does Llama 2 come in different types? So you see basically here we are asking types, but in the chunk the word that is present is different variants. So it basically like I mean we know that it semantically means the same thing, but when we see the syntax, when we see the actual words that are used, those are completely different, and that's why we want to build like a semantic search rather than a syntactic search, which is not based on the words, the actual words, but actually the meaning of the words. So that is where the concept of embedding becomes useful. So basically what we do is this query we'll convert in an embedding vector. Now embedding vector is basically like a vector, and a vector is just an array of numbers. So let's say 1 2 3 1, something like that. So let's say this is a 4-dimensional vector. What we'll do is we'll take the query string and we'll convert that to a vector. That process is called embedding. What this does is it allows us to represent text in a semantic fashion. So rather than just using the words in the string, we represent it using this vector, which we say that it represents the semantic meaning of the text. So for instance, this is a 4-dimensional vector. So like the example they give, like the first dimension may represent if it's like a temporal thing in nature. So if it has a temporal meaning, so something like day of a week, like Monday, Tuesday. So maybe this number will be high for Monday or something, or January or something, and others will be low. And maybe the second dimension represents if the word is an animal or something. So for dog or cat, this number will be high but others will be low. So this is just an intuition, but basically this is the idea. So we take the text and we convert it to embeddings, and in the same way in our retriever system, each of these chunks, these are also text chunks, and this will also be converted to embeddings now. So each chunk will be represented using a vector now. Each of these vectors will be present in the same fashion. So let's say there will be 4 numbers since we went ahead with the 4-dimensional vector. So each of these chunks will be represented using a 4-dimensional vector. And what we do is when we get this query, we get the embedding for that, and we take this embedding here and we find the distance of these vectors. There are different ways to get the distance, cosine similarity or Euclidean distance, or L2 distance or something like that. So basically what we do is we check which amongst the 4 is the we took the 4 chunks as well. So let's say there are 4 chunks in the document. We see out of these 4 chunks which is the closest, using this embedding that we have, which is the closest to the query, and that chunk is retrieved then. So in the example here, maybe when we say something like different types, that gets encoded in an embedding, and this different variants gets encoded in another embedding. Now when we do a similarity search using these embeddings, maybe this chunk will be retrieved itself directly, rather than doing a word overlap kind of algorithm. So the word types is not even present in this chunk. The word variants is present, but still we'll be able to retrieve the relevant chunk because of the semantic search that we have. So this is the idea. And when we implement this by ourselves, like let's say we code the calculating the distance and all, it has a very high latency. And to reduce this latency, what we do is we use something called as vector database. So it's something similar to the SQL database or the relational database that you hear of. What is different in vector database is it does some processing on these embeddings so that the query latency becomes very low. Let's say this vector database, what it holds is, let's say this is the database. What you will do is you will send the documents or chunks, and along with that chunks you will send the vectors as well. These vectors will basically be like embeddings, you can say. So this is what is saved in this database now. So there are chunks, text chunks, and the corresponding vectors to it. So this is how the database will be designed, and this database you can query using a query, but convert that into embedding first. So in a vector, and this vector you send it to the vector database for query, and it will retrieve the most relevant chunks that you want based on the semantics of it. So it's because we are using embeddings, we can say this is a semantic search. So we'll go and see in the code, we'll actually build a small retriever, and we'll understand these concepts more in depth. And once we build this retriever, we can go back and use that same retriever algorithm in our RAG framework, so that we can build a proper question answering pipeline. So let's jump to the code and understand these concepts even more through implementation. So before moving on to the code, just like how we use like a Postgres database or some sort of database for relational database, similarly for vector database also we need to use like a particular project. So it can be like an open source project or a paid one, depending on your requirements. So when I try to get this list, there are some particular vector databases that are available. So one is Pinecone. Pinecone is not open source, I suppose. You have to pay, I guess, to use it. And there are other, Milvus is open source, and there are other ones like Chroma and Quadrant, and some others keep coming up. So you can just have a look, and whichever one you want to use. We'll go ahead with the Chroma database that is there. That is a vector database, and let's go to the website. When we go to the documentation, so we can go in the getting started. So it tells you like you just need to install do pip install ChromaDB, and then you can start using it. So this is what we will do. We'll set up a ChromaDB client similar to the tutorial that it's telling us, and then we can create a collection basically using the client. We can use this collection to save our documents or chunks along with their vectors. So we can come here and we can add the documents. What I have done is, let's say for now we manually embed the documents. Let's say there are two documents here. So this is document 1 and this is document 2. These will basically be your chunks while using your RAG framework. But let's say you only have two documents to retrieve from, and these are its corresponding embeddings, let's say. So I've manually put these embeddings for now, but even these embeddings will be taken from an algorithm or a model or a sentence embedding model. Along with these embeddings and documents, you need to pass the IDs, and they can be unique for these documents. For now we have just made like ID1, ID2. It doesn't matter much, but maybe for specific use cases when you need the ID, and then you can query using ID as well. There it might be useful. Along with the documents, what you can do is you can save these metadata information along with the document. So this is like a JSON corresponding to each document, and you define the keys and the values for it. So whatever information you want to save extra with those documents, you can save it. So here they have given source as an example. You can also put like anything you want, like page number. Let's say if you are saving one page as one document, you can like mention page number, like get the page number, document here, and mention like page number as key and the actual page number. So that is one thing that you can do. What it allows you to do is you can start filtering based on the metadata, all the retrieved results. Maybe you want to query like top part of the document and not the bottom part. So you can say like the page number should be greater than the page number should be less than 10 if you want to query only from the first 10 pages, something like that. So you can take a call on metadatas and how to save it. Basically it will be very useful in querying if you have like a specific requirement. That's all. So we'll add these two documents for now without any metadata, and we have just given the IDs and we have manually added these embeddings for it. It's just a two-dimensional embedding for now, just for our understanding purposes. The next part is we can start querying this collection now. So it's that simple. Once we have added our documents, what we can do is we can send a particular query along with the embedding, and we can start retrieving the documents. Let me put a query here. I have not put like a textual query for now, but we are directly giving an embedding for it. This is also done manually. We can give the text as well. By default it will use some embedding model, even if we don't give this embeddings. By default in the documentation, if we go, it does use some embeddings internally. If you want, you can use the default ones. Otherwise, just to show you like how we can use the specific embedding model as well, we'll actually use a specific embedding model later on, and you'll realize like how we can do this. But for now, let's say we have the embedding somehow and we pass the embedding. So whatever the document that is closest to this, we want that. And end results means the top results. So we want only one document to be fetched or retrieved based on this embedding. So now when we print the results, so we see that it's giving document as the document 2. So this document was retrieved for this particular embedding. And why is that the case is because you see it's returning the distances as well, and it's saying the distance is 4 here. So what we can do is we can actually make number of results as 2, so that we get both the documents. Basically we know that our database only contains 2 documents. So when we get 2 results, it will return both the documents, but we will get to see like the distance as well. So we see the distances for the first document that was retrieved, which is the document 2, the distance was only 4, which is more closer. But here the distance is 10, which is for the document 1. So that's why if we take only the top one, document 2 will be retrieved. So let me explain a little like why is this the case. Just remember, we are adding 2 documents here with these particular embeddings. Now since this is a 2-dimensional vector, we can actually it's humanly possible to visualize and work out the math as well. So let's do that. So let's draw like a coordinate system, the Cartesian plane. Let's say this is the coordinates and this is the 0, 1, 2, and let's say this is the y-axis. Okay, I'm terrible at this. So what we are saying is, we are saying 1, 2 represents document 1. So coordinate 1 and 2 here is a document 1, let's say, and 2, 1 somewhere here represents document 2. So these are 2 vectors, you can say, where you can draw like these vectors from origin. So document 1 is represented by this vector, document 2 is represented by this vector. And then when we see like the query embedding that we are passing, the query falls on 4, 1. When we can plot 4, 1 here. So this is where the query is. We can like manually visualize this and see that document 2 is indeed closer to Q rather than document 1. But the way it's actually calculated is in ChromaDB. If we go to the documentation, I guess I saw it in the usage guide. Yeah, changing the distance function. So there are these distance function that we can set. There are these 3 distance function they are saying which we can set. L2, IP is inner product, and cosine similarity. And they are saying the default is L2. So this L2 is calculated like this. They have given the formula as well, from where the actual 4 and the 10, these distances that we saw, the 4 and the 10, these are coming from this particular formula for distance, and whichever will be the closer, that will be retrieved. So basically how the L2 is calculated is, when we go here, it's like for document 1, if we want to calculate the distance, it's going to be 1 minus 4, and this will be squared, and the other one will be 2 minus 1, and this will be squared. So this is the x-axis of document 1, x-axis of query, y-axis of document 1, and y-axis of query. And when we work out the math, it comes to 10. So 9 plus 1. So this is how we get the 10. For D2 also you can calculate. It's going to be something like 2 minus 4 squared plus 1 minus 1 squared, and this will come to 4. So this is how we get these numbers 4 and 10, which we got in the code as well, 4 and 10. You see, this is like very simple calculation that is happening in the backend, but we use vector DB because it performs these calculations very fast. Now when we have like many documents, right, not just 2, maybe we have like hundreds or even 200s or even more, but let's say like a 200 document retriever system, it has to take that query embedding and it has to calculate for each and every of those 200 documents to bring the retrieved document. And also the embeddings here, we have used 2-dimensional embeddings, but this can go like very big depending on the embedding model that we use. Typically these are like 700 or even 1000 dimensionals or even more, 2000 dimensionals as well. So in that case it becomes like the latency of retriever becomes very high, and we don't want that. We want the latency to be very low. That's why that's exactly why we use this vector DB. Right now in 2 documents we cannot see that, but you can just trust me maybe for this, that when you have many documents, still it will give you the results almost instantaneously. When we run this code, it runs almost instantly, right? So this is what will happen even if you have more documents and higher dimensional of vectors as well. So now let's talk about how do you get sentence embeddings as well. So for that we use sentence transformer generally. That's actually like a standard way to go. It's by default you can start with this, but it's not the most superior model out there. There are better embedding models that can be experimented with and it can be used. But for now, let's just go with the sentence transformers model that is there. So when we go to this, it's there on the Hugging Face, I guess. So this is the code that they are giving. We can use the same thing. So let me just load the model first. I can mention the cache directory here as well, because I want to save the model in a particular directory. So when we run this, it will start downloading the model in this directory. It's similar to how we download the language models as well, through Hugging Face. So it's in the same way this will also be done, and it's actually done. So I mean, next time when we run this, it won't download and it will just load the model from this folder. So let's give some example sentences as well. Like let's say we give 2 sentences here. The man is sitting on the tree, the girl is eating an apple, and we pass this through model to encode it, and we hopefully will get the embeddings here. So you see we are getting this embedding. It's not like it's printing the embeddings, but let's just print the shape for it. So when we see the shape, it basically has 2 vectors of 384 dimensions. So you see this 384 is the dimensions of one particular vector, and since we passed 2 sentences, it's giving those 2 embeddings for our 2 sentences. And if you want to see the embeddings, these are the embeddings. So somewhere here the first embedding ends, and this is for the second sentence. So you can actually see the embeddings as well, and this is what I meant by higher dimensions. Like depending on the model that you have, this uses this paraphrase mini LM L6 V2, but there are different embedding models as well. You can have like better embedding model depending on your use case and everything. So once we know how to use the vector database and we know how to get the embeddings, let's actually use these embeddings and push documents inside the vector database and actually build a retriever as well now. Before moving on, let me just rename this variable to embedding model so that we'll know which model is actually being used. So nothing changes, it's just the variable name that I'm changing. So now this is the problem that we have. Let's say we have these 3 chunks from, let's say, our RAG framework or somewhere. We got these 3 chunks. The chunk 1 says Llama 2 model comes in these many parameter variants, and the second chunk says Llama 2 chat is the dialog fine-tuned of Llama 2 base model, and the third chunk says Llama is safe to use since it limits generation of violent text. So this is just some information that we want to sort of index in our vector database. So first what we do is we create like these embeddings of these chunks. So we pass these chunks through our embedding model and we get the chunk embedding. So if you want to see the shape of this vector, it's 3 cross 384. So we have like 384 dimensional embeddings for these 3 chunks that we have. We have got those embeddings now. What we can do is we can create like a separate collection for this. Above we had created like my collection just for a demo purpose. We can create a separate collection here. Let's call it RAG Llama 2 or anything. You can name it anything you want, and this will be the collection that we'll use. And then what we can do is we can add these chunks in this collection. So this collection does not hold anything as of now, this new collection that we made, but now we'll add these chunk embeddings and these chunks. So this is a list of 3 text chunks that we have and the corresponding embeddings that we have. We'll also pass like dummy IDs you can pass. So this is just ID1, ID2 and ID3, and we'll add these 3 chunks along with the embeddings in the vector database. Now that our vector database is ready, what we can do is we can actually query it. So let's say, like an example here, our query is something like different versions of Llama 2 model. So this is our query, like we want to know about the different versions, let's say, and someone has put the query like this. We can take the query and we can make the query to the collection here. The collection is basically our vector database that we have done. But while passing the embedding, what we'll do is we'll take this query and we'll again pass it through our embedding model so that we get the embedding for it. So basically we just had these chunks and this query and we passed it through the embedding model. The chunks were passed through embedding model and saved in the vector database, and the query is passed through embedding model, and that embeddings are used to query the vector database. And we are saying only return one result. So let's see what it returns. So it returned this chunk that we had, which is basically talking about the variants of the Llama 2 model, which is fairly correct retrieval, considering this talks about the variants and these two talks about like the Llama 2 chat and the safety guidelines and all. So you see this word versions was not even present in this chunk, but still it was able to say that he is asking about this chunk. So this is what a semantic search is. Maybe you can try a different query here. Let's say some query like what about offensive messages? So like let's say we are building like a retriever system for specific to Llama 2, and someone comes and asks this kind of query. So now when we run this query, it says Llama 2 is safe to use since it limits the generation of violent text. So you see, it's this term offensive messages was not even present in the chunk. It was still able to determine that hey, you're asking about this text. Next, what we can do is we can use this retriever, and we can use this retrieved text to pass it in some LLM along with this query again, and we can build like a proper answering system which will generate the answer based on this retrieved text as well. Just to show you what we can do is we can make number of results as 3, and you can see like the ranked a list of these 3 documents, how the distances are changing. So this is 58, this is 84, and this is 97. So it's because this distance was the lowest, this top result was retrieved. But if there are many, you can also get like top 3 results and so on, and then you can use those top 3 results rather than just using one. It's basically like how we make Google search. We sometimes may not rely on the topmost, but the second or the third one as well. So similar to that, even this method of semantic search is not perfect. It does fail many times. Even the topmost results is incorrect. We'll see in the when we actually build the RAG pipeline, we'll see some examples and how actually it works, maybe in the next video. There's just one thing I would like to show you. There is something called as MTEP leaderboard. So this is again by Hugging Face. Oh sorry, it's MTEP. This MTEP leaderboard, you can use it for choosing which embedding model you want. So you can see this massive text embedding benchmark. This is the leaderboard that is there, and there are different models here. So for example, E5 Mistral, and it says like what are the embedding dimensions for it. This is 4,000, around approximately 4,000 dimensions, which is around 14 gigabytes. And the sequence length. So sequence length is basically the limit of tokens that you can send. You can only send this model 32,000, around 32,000 tokens, and only for that you can get the embeddings for. So even there's a limit for that. Even this model that we used, the mini LM model, even this must be having some limitations. We should check what are the limitations and all. So we can't get embedding for like a huge text as well. We can only get embeddings for a certain window of text that is there. So it gives these scores, and based on this, whenever you're using, you can always refer to it to check which embedding model you want to use to get the embeddings for. One more point, these embedding models are generally for English language, but there are certain embedding model like this Coher embed model for multilingual as well. So depending on that, like if you're working on different languages, you can also consider using these different models which works on multiple languages. So yeah, that's about it. In the next video, we'll actually put all of these things together, or whatever we have discussed till now, the retriever system we'll use, and we'll build like a proper RAG pipeline which takes a question and gives the final answer, not just the retrieved text. Maybe consider liking and subscribing as well. Yeah, see you.